So in this lecture, I will show how to check deflection for slabs in ETABS. For first, let me see what is deflection. So deflection is vertical distance between the original axis of the beam and the elastic curve is called a deflection. So this is your original axis of beam, and here is your elastic curve. Elastic curve is nothing but a deflected shape of the beam. So it is nothing but your deflected shape is called as elastic curve. So I will repeat it once again. The vertical distance between the original axis of the beam and the elastic curve is called a deflection. So this is your original axis of the beam, and this deflected shape, it is elastic curve. The vertical distance between these two is called as deflection. So we call this as deflection. So deflection is denoted by delta, and it is measured in millimeters. So deflection, which is denoted by delta and measured in millimeters. So deflection depends upon many factors. So one of which is external load. Next, span of the beam. Span of the beam or slab. If you have larger span, so you will have a more deflection. Next, cross section of the beam. So nothing but width and depth of the beam. So next factor will be Young's modulus or modulus of elasticity. So which is denoted by E. So modulus of elasticity is nothing but a type of material. So either material, it may be concrete, steel, wood, or pre-stressed. So different materials will have different Young's modulus. So last factor, it will be support condition. Support condition or boundary condition. So these will affect the deflection of a member. So in the next, let me see. So from IS 456 2000 and clause number 23.2 in page number 37. The two clauses mentioned from IS 456 2000 provide guidelines for controlling deflection. See, here it is the clause 23.2, control of deflection, in which you have two clauses. One is first A. So this clause, the final deflection due to all loads including the effects of temperature, creep and shrinkage, and measured from the as cast level of the support of floors, roofs and all the other horizontal members, should not normally exceed span by 250. So this criteria will be used. The deflection is measured from the as cast level of the supports, which is the level of the supports when the structure was initially constructed. So the criteria is span by 250. So next, the second criteria will be, so this one, second criteria. It will be used deflection after erection of partitions and finishes. So it is span by 350 or 20 mm, whichever is less. So here span means in case of slabs it is always shorter span. You need to consider the shorter span of the slab. So for deflection check, we consider, or it will be for service limit state, which means dead load plus live load. So this is your serviceability limit combination. So these two are permissible deflection or allowable deflection. So these two are permissible or allowable deflection. So this case 1, it is without partition or finishes. So this second criteria, L by 350, it is with partitions or finishes. So you should remember these two. In case of slabs, deflection is checked with respect to shorter span, and it is for service limit state, that is dead load plus live load. So let me consider an example. So I will take a simple model. Here my this x span, horizontal span is 6 meter, and my vertical span, this is 8 meter. So columns are 300 by 300 millimeter. So beams are 200 by 450 millimeter. So slab thickness. So thickness of the slab is 155 millimeter, and loading. So dead load 1.5 kilonewton per meter square. Live load 2 kilonewton per meter square. So mesh specifications. I have used rectangular mesh of size 0.3 into 0.3 meter. So and floor to floor height. Floor height is 3 meter. So in this case, first let me calculate the allowable or permissible deflection. So it should be span by 350. So here in this case, span is always shorter span. So here the shorter span is 6000 millimeter. So divided by 350. So 6000 divided by 350, it will be 17.14 millimeter. So it will be 17.14 millimeter. So this is your allowable deflection or permissible deflection. So next, whatever the deflection from ETABS. So let me check it. I made the same model as I said in the earlier. So just I will run the analysis. So go to display, deformed shape. Here combination, you should select dead load plus live load. In case of draw contour on object, so you should select displacement UZ. So apply, close. So yeah, this is the deflected shape of the slab. So you just move your cursor. So UZ, it is minus 19.769. So your ETABS deflection is 19.769 millimeter. So ETABS deflection is nothing but your actual deflection. Actual deflection. So in this case, so actual deflection is more than your allowable deflection. Will you accept it? No, because your actual deflection in the structure is 19.767 millimeter, so which is greater than, so allowable deflection is, or permissible deflection is 17.14 millimeter. The code permits or allow 17.14 mm to deflect, but the actual structure, it is deflecting by 19.767 millimeter. So it is more than the allowable deflection. So you can directly say the slab is failed in deflection check. The slab is failed in deflection check. So next, what is the solution? So solution is, you can increase the thickness of the slab. So first solution is increase thickness of slab. So next, second, increase number of elements, which means increase the number of beams or columns. So let me try this with, so I will increase the slab thickness. So first I used slab thickness of 150 mm. So next I will increase the slab thickness to 200 millimeter. So let me go to ETABS model. So first unlock the model. So go to define section property, slab section. So add new property. So slab thickness is 200. So grade of concrete, you select M20 slab. So here the thickness is 200. Okay. Okay. So you select this slab, go to assign shell slab section. You select S200, which means 200 mm thick slab. Apply, close. So let me run the model. So run analysis. So now let me check the deflection. So go to display, deformed shape. In combination, you select dead load plus live load. Show contours, it should be used. Apply, close. So now the deflection is, so it is showing 15.289. So in this case, actual deflection is, so let me note it, 15.289. So this is the actual deflection. So your allowable deflection, it is same L by span by 350. So your span is shorter span 6000 divided by 350. So it is 17.14. So now the code allows the slab to deflect by 17.14 mm, but the actual deflection, it is 15.29. Hence the slab is safe in deflection. So what is the condition? So your actual deflection should be less than your allowable deflection. Hence you can say the slab is safe in deflection. Here actual deflection is 15.289, which is less than allowable deflection. Allowable deflection as per the code is 17.14. This is acceptable. So when I increase the thickness of the slab, so the deflection is controlled. I will try the second method. So what is the second method? Increase number of elements. See here. So your actual diagram, your actual model is, so this span is 8 meter. At the center, I will introduce two columns. So at a distance of 4 meter, I will introduce columns here. So similarly here, I will introduce a column at a distance of 4 meter. So I will divide this span. Initially it was 8 meter. Now I will divide this to 4 meter and 4 meter. So let me check it. Same. You unlock the model. Okay. So go to quick draw columns. So column size is 300 by 300 millimeter. Here I am unable to see the midpoint. So for which go to draw, snap options. You select line ends and midpoints. Apply. Okay. See here. Now you can, it will indicate midpoint. So I will introduce one column here, one column here. Now the span is divided into 4 meter by 4 meter. So let me check the dimension. See here. From here to here it is now 4 meter. 4 meter. So let me run the model. So run analysis. So go to display, deformed shape. In combination, select dead load, live load. show contours, that is UZ, apply, OK. So now see the deflection. It is decreased to minus 5.54. So here in this case, actual deflection is 5.54 millimeter. So as per the code, allowable deflection is same, span by 350 means 17.14 millimeter. So in this, the code allows to deflect the slab by 17.14 millimeter, but actual deflection was seen, it is 5.54 millimeter. So in this case also, in second case also, your actual deflection is less than allowable deflection. So actual deflection, it is obtained from ETABS results. It should be less than allowable deflection means it is from code. So span by 350. So in second case, so actual deflection is 5.54, which is less than 17.14. So hence you can say that the slab is safe in deflection. So like this, you can optimize the things. You can increase the depth of the beam. So finally, it should be well within the limits.